Hello and welcome to Engineers Mindset Academy. So in the previous video, we introduced Cauchy's residue theorem and we solved two problems to actually explain the residue theorem. In this video, let's consider this question on the board. It says, evaluate z squared minus 2 dz all over z multiply z minus 1 multiply z plus 4, where c is a cycle, z equal to 2. And mind you, in each of these integrals, you can actually use Cauchy's integral formula to solve, or you can actually use the Cauchy's residue formula to solve. So anyone that is convenient for you, you can actually use any of them to solve. But this video is targeted to explain the use of Cauchy's residue theorem to evaluating this integral. Now, the Cauchy theorem, residue theorem simply states that the integral of a function f of z multiplied by the z is equal to 2 pi I multiplied by b1, where b1 here is the residue itself. And to find the residue b1, we simply use the relationship b1 equals 1 all over n minus 1 factorial limit as z tends to a, the n minus 1 all over the z n minus 1 multiplied through by z minus a to the power of n times f of z, okay, times f of z, times f of z, where f of z is a given function, n is the order of z upon factorization as the denominator. Mind you, the order of z as the denominator upon factorization. A itself is the pole of the denominator. Now, to obtain the pole, I've always said, you have to just equate the denominator to 0. That's how to find the pole. Now, having this now, let's compare these two equations. This is integral of f of z dz. You have the integral sign, you have the integral sign, you have the z, and you have the z. This simply means that f of z is now what? The function in between here. So this simply implies that f of z is equal to z squared minus 2 all over z into z minus 1 into z plus 4. You have this. So this is our function f of z, and of course upon comparison that becomes the function f of z. Okay, now we need to find the poles. To find poles, okay, you simply equate the denominator to 0. The poles now is a, you equate denominator to 0, so we have z multiply z minus 1 multiply z plus 4 to be equal to 0. And by factorization, if I have something like this equal to 0, then it simply means that z itself is equal to 0 and z minus 1 is equal to 0 and z plus 4 is equal to 0. So if you do this, z is equal to 0, simply send minus 1 over to this side of the equation. Negative sign plus an equal sign becomes positive. So I have z is equal to 1. Finally, z is equal to 10 plus 4 over here. Positive sign plus an equal sign becomes negative. I have z is equal to minus 4. So this simply means that the poles, okay, this simply implies that the poles are A equals 0, 1, and minus 4. So A stands for the poles. Okay. Now, have you found this? Already this is factorized. Since it is factorized, then what is the highest power of z? As the denominator, the highest power of z simply was 1. All of them here are to the power of 1. So which means the order, which is n, order n is simply equal to 1. After factorization, the highest power of z becomes the order, and this is already factorized, so z is equal, n is equal to 1. Now, having found this, the next thing, another condition was given. They said where c is cycle, z equal to 2. So we need to check if these poles falls within the cycle. If the poles falls within the cycle, then we can go ahead and use the Cauchy's residue theorem to solve for all of them. But if they did not fall within the cycle, or maybe few did not fall within the cycle, then we cannot solve for that few which did not fall inside of the cycle. Okay, so to check if these poles are within the cycle, you were given your cycle Z to be equal to 2. And I explained when we did complex analysis or analytic function, I said this simply means Z plus 0 to be equal to 2. I said that Z is always or usually attached with a number, always attached to a number, and that number tells us the center of the cycle where we always consider to be the central point. Then we can take our radius from there. So if this is Z plus 1, then it means that the center would have been 1. But since we weren't given a center, it's just Z, then it simply means Z plus 0. So 0 becomes the center. This is the center of the cycle, and this remains the radius. Always this remains the radius of the cycle. So we now plot our cycle. Okay, this is our complex plane. We plot our cycle on our complex plane. Remember, this is the complex variables I, and of course this is minus I. Now, since we don't have a complex variable for the pole, we don't have any complex number here. All we have are real numbers 0, 1, and minus 4. Okay, this plane represents the real part of the function Z. So these are the real numbers and these are the imaginary numbers. Alright, so we need to find if the poles falls within the cycle. The center is 0, this is 0, the radius is 2. So from the center, you plot out 2 on both sides. This is 1 and this is 2. Also, this is 1, this is minus 1 and this is minus 2. That becomes the radius. With this radius now, you can plot the cycle. Okay, you have this. Sorry, the cycle is not that accurate, but you have something like this. So from the center, radius is 2 and radius is 2 on both ways. Now, we have to confirm our poles are 0, 1, and 4, minus 4. You have here to be the origin, 0. 0 is inside the cycle. You have plus 1. Plus 1 is inside the cycle, but 4 is not inside the cycle. Minus 4 should be somewhere around there. This is minus 3, and this is minus 4. If I proceed it as well, notice that minus 4 and plus 4 are not within the cycle. So we are going to what? Discard minus 4. The residue theorem under this cycle for minus 4 does not exist. It's going to be 0. So we only pay attention to what? 0 and 1, which falls within the cycle. Okay. So we can only solve for 0 and 1, which falls within the cycle. Alright, so let's start over here. So considering the first pole now, when A is equal to 0, that is the first pole, then the residue B1 is equal to 1 all over, remember, 1 over n minus 1 factorial, and n is the order n is equal to 1. So this becomes 1 over 1 minus 1 factorial, the limit as z tends to a. Limit as z tends to a, and a now we are considering when a is equal to 0. So this becomes limit as z tends to 0, the n minus 1 all over the z n minus 1. And what is n? N once again is equal to 1, which is the order. So this becomes the 1 minus 1 all over the z 1 minus 1, now multiplying through by, remember, z minus a to the power of n. So you have z minus what is a? A is 0 in this case, so z minus 0 to the power of n. N again is 1, so to the power of 1 multiplied by the function f of z. What is the function? Remember, we found out that the function is equal to this, z squared minus 2 all over the whole of this. So multiply by the function z squared minus 2 all over z into z minus 1 into z plus 4. You have this. Okay, so B1 is equal to 1 all over 1 minus 1 is 0. So I have 0 factorial limit as z tends to 0 of the 1 minus 1 is 0. So I have the 0 all over the z 0 into z minus 0 is z to the power of 1 remains z times, you put down your function, this is z squared minus 2 all over z into z minus 1 into z plus 4. So you observe here now that z can actually strike z. So that is off. I have that b1 is equal to 1 all over 0 factorial is 1, so it becomes 1 over 1 limit as z tends to 0 of any variable to the power of 0 remains 1. So d to the power of 0 is 1, dz to the power of 0 is 1. So I have here to be 1 all over 1 multiplying through by, I have z squared minus 2 all over. So I'm left now with z minus 1 times z plus 4. Okay, so 1 over 1 is 1. Then this becomes limit as z tends to 0 of z squared minus 2 all over z minus 1 into z plus 4. Now, this is simply saying wherever you see z, put in the value as what? 0. So, this simply implies that the first residue, b1, is equal to, this is z squared, but z is 0. So, you have 0 squared minus 2 all over, you have z minus 1, z is 0, so it becomes 0 minus 1 times z plus 4, 0 plus 4. This is equal to 0 squared is 0, 0 minus 2 remains minus 2 all over 0 minus 1 remains minus 1 times 0 plus 4 remains 4. So this is actually minus 2 all over minus 1 times 4 is minus 4. 2 here is 1, 2 here is 2. Minus cancels minus, so I'm left with 1 all over 2. So this simply implies that the first residue, B1, is now 1 all over 2. Okay, the first residue is 1 all over 2. So let's keep that aside somewhere. Okay, so we have the first P1 to be equal to 1 all over 2. Let's solve for the second case now. When A is equal to 1, okay, these are the only two that fell into the pole. When A is equal to 0 and when A is equal to 1, we can't solve for minus for the value is 0 since it doesn't fall within the cycle. So we consider now when A is equal to 1. We can still do that over here. So when A is equal to 1, which is now the second pole, then residue B1 is equal to 1 all over, remember, n minus 1 factorial, n once more remains 1. So you have 1 over 1 minus 1 factorial limit as z tends to A now is 1. So as z tends to 1, the n minus 1 becomes the 1 minus 1 all over the z 1 minus 1 into, you have z minus A. So this is z minus A now is 1, so it becomes z minus 1 to the power of n. N still remains 1 times f of z. And what is f of z? The given function, we already found it to be this, z squared minus 2. So multiply z squared minus 2 all over z times z plus z minus 1 times z plus 4. You have this. Okay, so B1 is equal to 1 all over 1 minus 1 is 0, so I have 0 factorial limit as z tends to 1. The 1 minus 1 is 0, so this becomes d to the power of 0 all over the z to the power of 0 into, okay, so from here you observe that z minus 1 and z minus 1 can strike. So z minus 1 strikes z minus 1. I am now left with z squared minus 2 all over z into z plus 4. You have this. So b1 is now equal to 1 divided by 0 factorial is 1, limit as z tends to 1, d to the power of 0 is 1, dz to the power of 0 is also 1, 1 over 1 is 1, 1 multiplies everything here remains z squared minus 2 all over z into z plus 4. Okay, so this simply means wherever you see z, put in the value as what? 1, limit as z tends to 1. 1 over 1 is 1, 1 times this remains everything there. So let's now substitute the value of z as 1. So I have z squared here minus 2. In place of z, z is 1. So this is 1 squared minus 2 all over. I have here z, and z is 1 into z plus 4. 1 plus 4. This is equal to 1 squared is 1, 1 minus 2 remains minus 1 all over 1 plus 4 is 5, 5 times 1 remains 5. So the second residue, B1, is also minus 1 divided by 5. We have this. Now the integral of that function, we said integral of f of z from Cauchy's residue formula is equal to 2 pi I times b1. Now, if you have different regions or multiple regions like we've done so far, and we have two values of the residue, then this is going to be what? Plus the second residue, also 2 pi I times the second residue b1. You can use B1 and B2, but I think the theorem is simply B1. Okay, but then this is equal to 2 pi I times the first B1, first residue is 1 over 2. So you have times 1 all over 2 plus 2 pi I times second residue is minus 1 over 5. You have minus 1 divided by 5. So this is equal to, from here, 2 cancels 2. I have pi I multiplied by 1 remains pi I. Okay. Now this is minus, so minus 2 over 5. So you have 2 over 5 pi I. Okay, so you can actually go ahead to evaluate this. This is pi I. Pi I simply means 1 pi I minus 2 over 5 pi I. So you can actually evaluate that. Let's do a rough sketch here. 1 minus 2 all over 5. 5 is the LCM, so you have 5 minus 2 divided by 5. This will give you 3 all over 5. Okay. So this simply means that the integral of f of z dz, which is this function now, is simply equal to 3 over 5 pi I. That becomes the answer to that given question. Alright guys, so that's it on Cauchy's residue theorem. In the next video, we can come up with more examples. Okay, I'll see you in those videos. Thanks and cheers.